Guys, so let's start. Good evening. My name is Alexandra Boguslavska. I'm CEO founder of Data Science UA, and I'm so happy that you are on our online meetup, NLP and healthcare challenges and opportunities. Our absolutely great speaker, Enrico Santus, senior data scientist from company Bayer from USA. Good morning, Enrico. In Ukraine, it is good evening. In USA, good morning.
Good morning.
Good morning. We are so happy to see you. I will tell you a little bit about our company, Data Science UA. I think most of our participants visited our courses, events, conferences. For whom is first time on our event, I will tell you more. We started 4 years ago in 2016. We organized first data science and AI conference in Kyiv. The name of conference Data Science UA. Now we organized 9 data science UA conferences. Before quarantine, of course, everything was in Kyiv. Now, of course, everything is online. That's why we can invite so amazing speakers from USA, from Canada, from Europe. What is we can invite everybody, all participants and speakers. As you know, we organize corporate trainings about data science and AI for companies. We have mentorship about data science and AI. And we have our great recruiting team. Our main focus data science and AI positions, but we can close absolutely all IT positions. We can close front-end, back-end, QA, C-level positions. Please meet our great team. Nastya, Alena, Alexandra, Bogdan, Oksana, Ira. And we have, you can see some of our open positions. Now we are looking for data engineer, senior data analyst, machine learning engineer, senior 3D developer, senior video processing software, CTO for computer vision company. If you are interested in some our open positions, please write me or our recruiters. We will be very happy to find something very interesting, especially for you. We have consultant track. Our head of consultant track, Nika Tamaya Flores. Our consultant team will be happy to help you with business analytics, data collection, data warehouse, data mining, advanced analytics. If you have data, we know what we can do with your data. Please write me or Nika. We will be very happy to discuss all details. As I said before, we have a few courses about data science, and we can do specially customized course based on your needs. And this year we opened a R&D center for our partners from USA. Now we have great team of computer vision, machine learning engineers, and we are interested to help companies, startups to grow, and we can help with a team of very talented engineers here in Kyiv in Ukraine. Please, you can see our social networks. We have YouTube channel, we have Telegram, Facebook. Please follow us. We always have great news about data science, AI, about our events. Please, I will be very happy to be in touch. Write me if you need something about data science and AI. And now, please work to our amazing speaker, Enrico. How are you? How is the situation now with data science and Bayer? Please tell us.
Hi. Thanks a lot. Thanks for the inviting, and happy to be here, and really happy to meet you all. And the situation in Bayer is that Bayer is realizing, as every other pharma company, that data is crucial. So we are currently investing a lot in analyzing data. My background then comes from academia. I used to be a postdoc for many years at MIT. I used to work in Asia, in Europe before then. And so data science, machine learning, deep learning, and particular natural language processing are crucial topics I've been working with since about 8 years or 9 years. So that's little bit what's the situation.
Thank you so much for coming, Enrico. And of course, everybody will ask about data about coronavirus, of course. And if you can share some news, maybe you know something from Bayer, it will be very great, because I think it will be a lot of questions about that, of course.
Yeah, no, we are not working on the vaccine, so I cannot share any special insights on that. I'm also on the spectator side for this. I'm waiting the vaccines to start becoming effective very soon, and hopefully this will take us from this very sad situation.
Okay, see. Let's start. Thank you for coming one more time. Let's start, guys. We have chat here in the Zoom. You can write where you're from, what are you doing. Maybe you have questions to Enrico, and after presentation, Enrico will answer all your questions. Please use our chat, of course. Okay.
Thank you, Sandros. So, do you see my presentation?
Yes.
Yeah, we see everything.
Great. Okay, so thanks again for the invitation. As you were saying before, I'm a senior data scientist at Bayer. I joined Bayer in 2020, January 2020. And before then, I had a long experience in the academic world. I worked in King's College of London, University of Pisa, the Singapore University of Technology and Design, the Hong Kong Polytechnic University, and then finally MIT. Among the other things, I've also worked at projects for Microsoft before, Lionbridge, which is a localization company. I've also worked somehow in art. I collaborated to the creation of a robot that was designed by Dimut Stribe. And it's a robot that prays and that generates through natural language processing original prayers that didn't exist before. And it's very funny to hear. It's a robot that utilized GPT-2, and it was exposed at the Centre Pompidou of Paris. And in the same period, I've also worked for the fact sheet for the US Congress about artificial intelligence. You can find it online. It's distributed by Harvard, the Bethel Center. And finally, in September 2019, I was invited to speak at the White House about natural language processing and artificial intelligence. So this is just to give a little bit of a context of what I will be talking about during this talk. So at the White House, I was speaking about how natural language processing was helping the administration. Today, I want to speak about how natural language processing can help healthcare. Indeed, the recent pandemic has shown us that our healthcare systems are very fragile, and we have to work to make them more sustainable by increasing their efficiency and effectiveness. And this can happen only by using data-driven approaches. You probably know better than I do about the opportunities that these approaches can do for optimizing the processes and rationalize the allocation of the resources. And finally, moving the healthcare from caring to preventing, and possibly to personalization, such that we can also basically address individual problems in a more specific way. So let's start this journey together. So historically, humans have always looked at correlations between events, and sometimes also in some very funny ways, right? Attempt to predict how events are correlated with each other. Already 4,000 years ago, in the city of Mary in Mesopotamia, there were stories about women whose lips could speak the word of God. And this was the pre-talk about what became afterward the oracles. The oracles passed from the Egyptian towards the Greek civilization, and they became so crucial in the Greek civilization that they are basically figures that are fundamental in the literature, in the Greek literature. And here you can see on the left side a picture of the Delphi oracle, which is super famous in this sense. At the time, the oracles could try to predict the future by looking at some natural events. For example, looking into the gut of the animals, of dead animals, or maybe looking at the leaves of the trees and so on, or the wind. Although this make us smile today, you have to think that still, especially in Italy, and I am originally Italian, so I can say that people still believe that they dream the numbers of the lotto that you see here on the right? So they try to correlate their dreams to something that is going to happen in the reality. And of course, there's no correlation there that is provable scientifically, but people still believe in that. So we advance pretty much compared to the Greeks, but still we have this kind of need of correlating events in a certain sense to understand the reality. In the complex reality of today, this is even more important. Taking informed decision is crucial in many aspects, and prediction and decisions, as I'll show you in a minute, are very much related. Imagine if you can predict the stock market of tomorrow. You're gonna do very great investments. You're gonna make a lot of money, and then like you're gonna get a good life possibly. Or also you may want to predict the disease that you are going or I am going to get in the in the future. These predicting this disease allow you to prevent it, right? You know that if you keep eating beef, maybe the risk of getting cancer will increase, so you avoid to eat beef. So predictions are crucial. And again, now we cannot do this kind of predictions anymore by looking at the gut of the animals, of dead animals, but we have to utilize very powerful statistical systems that can analyze historical data, and from the historical data get some insights and possibly predictions. So that's what artificial intelligence is trying to help us with. Predictions are highly tied to decisions, as I said before. In fact, whenever we take a decision, and let me tell you that every human being takes about 1 million decisions per month. Whenever we take a decision, what we do basically is we project the reality in the future, and then we pick the best of the various scenarios, right? We try to favor the best scenario. So that's what we do when we take a decision. So having a good model that can make all the possible predictions is definitely the best way to decide properly. As you can imagine, this capability is crucial in the industry. And if in some industry this capability is crucial for the revenue, for some other industry this is crucial also for human health and particularly human lives. As you have witnessed in the last year, in 2020, the countries, for example, that could utilize the data first and exploit it in the proper way, they were able to create the right protocols and save lives in better than other countries that didn't rely on data. So this is an important point. But making the right decisions requires also to have the right information. So whenever you want to go from a point A and a point to the point B, you want somehow to learn how you can get to the point B, right? And just as an analogy, you can imagine that you want to have a map. And similarly, if you want to achieve a goal in your industry, you want to find a way to achieve your goal, correct? So this is an analogy between reaching a goal and moving towards a point A, towards a point B. If you have a map like the one that you see in this screen, definitely it's very unlikely that you will be able to reach the goal, because you're gonna get lost on the way and you're gonna get in trouble. Probably if you have a map like this one instead, you have many more chances to get to the goal. Maybe you get lost a little bit on the way, maybe you lose time, you waste energy and so on, but at the very end, you may actually make it. And similarly, if you have more data and so a much better defined way to get to your goal, then you're gonna reach it without wasting time, energies, and resources. And that's what data-driven approaches are trying to provide us. So they look into historical patterns, experiences of people that had to do the same way before, and try to give us insights about how to get to the goal and generate actionable knowledge. And this is possible thanks to big data. I mean, we are all familiar with this, and you know that big data is characterized by velocity and volume. Velocity, just to give you some example, 90% of the data was generated in the last 2 years, with a 50 per growth per year between 2010 and 2020. Just to give you some number, we sent about 2.9 million emails per second. We produce 20 hours of YouTube videos per minute, and we post 50 million tweets per day. So that's a huge volume of data that we produce, right? We do it very fast, and we produce a huge volume. And this volume is about 44 zettabytes as of today. And if you were to save all this data into iPads, for example, or other tablets, you could create 6.6 stacks of tablets from the Earth to the Moon. So this is just to give you quantify the amount of data that we are actually storing. But are we utilizing actually this big data? The truth is that we are not utilizing. According to McKinsey, 90% of the business decisions are still made on the basis of the education, instinct, and gut feeling of the decision makers. And this is even true in healthcare, where 2/3 of the healthcare decisions are rarely based on data, according to PwC. And the reason is that whenever we think about data, we imagine Excel files that are very well sorted. We imagine charts, linked information, and so on. The truth is that big data is more likely like this. It's messy to analyze, it's difficult to understand, and so there's not many insights that we can actually gain for such a complex and unstructured reality. So we arrive at a point in which we are overloaded with data, but yet we are underinformed. And the reason is that on top of these two V's, velocity and volume, there are other two V's that nobody mentions. These are variety and veracity. Variety is the fact that most of the data is produced from people to people. So it's produced for humans. Humans read this data in a sequential way. It needs to be in the shape of texts, or in the shape of images, in the shape of videos, and so on. But this kind of unstructured data is not usable by machines. Also, it tends not to be interoperable or aggregated. It's hard to aggregate this data. The other V that is crucial to keep in mind is the veracity. So the veracity is crucial because data contains bias. For example, there are some categories that are overrepresented or underrepresented. This can be gender, can be race, it can be other things that we are not even aware of. There is noise in the data. So sometimes there is so much noise that the signal gets lost. So, and if we utilize the data, we get garbage in, garbage out, right? And it's very classic way to say in data science. And also there are some anomalies which sometimes are malicious, such as the fake news, which try to somehow diverge you from the real signal. And because of the poor quality of data, according to IBM, the US wastes about $3.1 trillion. So again, it's a huge, huge cost. So let's focus a little bit more on the healthcare domain, where about 80% of the data is unstructured. And you can see in this chart that you see the available data that is growing in a kind of exponential way. And then you see what we are able to do with the data, which grows in a linear way. And this means that the more the time passes, the larger the gap will be between the data that is available and what we are actually able to do with it. Another absurd statistics in this sense is that on top of being 80% unstructured, we invest, especially the physicians in the US. I mean, most of the numbers that I speak about will refer to the US, but they are generally generalizable also to the rest of the world. But in the US, a physician spends about 51% of their working time in writing notes, meaning that they only dedicate 49% to the patient, actually. The rest is writing notes. And there's the paradox that in 65% of the encounters that they have with the patients, they have no time to go through the notes before meeting the patients, meaning that actually this data that is produced is not even utilized. This means that we are basically creating millions and millions of data points, EHRs, insurance claims, radiological images, voice recordings, and so on, which contain socioeconomic information, patient medical histories, diagnosis, treatments, genetic information, and so on. And they are there for the benefit of no one. Exactly for this reason, one of the major cause of death in the United States is medical errors. Medical errors comes as the third cause of death after cardiovascular problems, oncology, and then there are the medical errors with 250,000 people died per year. And about, I don't know now exactly the percentage, but a big part of them are kind of avoidable. They are coming from adverse events or other things like that. Just to give you another perspective of this number, 250,000 deaths is similar to what to the total of deaths caused by COVID in the United States in the last year, in 2020. So we're talking about huge numbers. So what can we actually do to play around it? We have some problems, we know we have them, and we have to face them. So the first thing we have to do is to get this unstructured data and try to turn it into structured data, which is interoperable and aggregated. So structuring the information through text mining. And then after we have this aggregated data, we can explore some hypotheses and business questions to find some actionable knowledge from which we can actually gain either in terms of revenue or in terms of cures, treatment, and so on. As of today, most of the first step, the turning down structured data to structured, is done manually, utilizing human beings. But human beings are very slow. They can read maximum 1,000 words per minute if they are very good. And they have an understanding of 85% if they are very good. So meaning that if they had to read the full big data, they take ages. So this is not even considerable as an option. For this reason, there are other solutions that this is what I will speak about in a second. So for this reason is most of the decisions that are taken today in the healthcare domain, especially for what concerns oncology, are based on only 3% of the population that participate to clinical trials. That means that whatever we learn about this 3%, then we generalize to the remaining 97%. And I mean, I'm not very sure this is the right way to move on in the future. What we would like to have is something a little bit more fine-grained, right? Because if you look at an image like this one of the Mona Lisa with only 3% of the pixels, I mean, you won't enjoy it very much, you won't understand it very much. And similarly, we are looking at diseases today by looking at very few data points. And that's not enough to understand the diseases. What we want is something like what you see on the right side, like Mona Lisa with high definition, high resolution, and you want to look at the diseases with high resolution too. So this is enormous opportunities for the healthcare domain. It can help to address the problems like risk prediction, early diagnosis, treatment discovery, patient selection, and so on. And this will definitely move us towards a personalized and preventive care. And the technique to get to that is using natural language processing. So you all know, you all have heard about this technique that has recently made a lot of news. And it's basically a subfield of artificial intelligence that aims at manipulating, understanding, and generating human language for a number of purposes, which healthcare is one of them. It exploits, of course, machine learning, and in particular deep learning most recently. And since I worked in academia, in particular in MIT and Bayer, I've been utilizing natural language processing for many goals. For example, for turning hard copy documents to digital form, through optical character recognition, OCR. I have organized these documents in categories given what these documents were about. I have utilized algorithms to extract information from these documents and fill such information into tables such that people could do retrospective studies to understand better some diseases. And I try to do fake news detection, so finding claims, check whether these claims were trustable or not by verifying their veracity. Remember, veracity is one of the 4 V's I described before for the big data. And finally, I've utilized the data that were extracted and verified to perform some clinical purposes. In particular, patient selection, patient matching to some treatments. So let's get into some of the use cases I really worked on, and maybe this give you some perspective about what is possible. In 2019, in a collaboration between MIT and MGH, we developed a convolutional neural network to extract information from 25,000 breast pathology reports. These breast pathology reports were originated in 7 hospitals, and the idea was twofold, right? It was on the one end to automatize this without using rules, because rules are not very accurate, and they are also unable to generalize across institutions. And the other goal that we had was to create a system that could in fact generalize across institutions, such that other new institutions in the future could utilize the same system. So extracting information from medical notes means to look into a free narrative and identify some very specific pieces of information, such as the tumor location, the histology of the tumor, and the sites, and so on. This is on the left. You see what we have done. You see an example of a medical note, and on the right you see the information that was extracted. And information was extracted as present as absent. So you see, we go from unstructured data to structured data. The 7 hospitals were 5 from the Boston area, so the MGH, BWH, and so on, and 2 out of the Boston area, 1 from Detroit and 1 from Pakistan. The population, as you can see, was women, mostly in the period from 87 to 17. The majority of them were white, and there were also some minor representation for the other races. The system that we developed was a convolutional neural network that turned the node into a matrix of embeddings, so and a tensor. You can see it here. You see on the top left the node, and then you see how it is turned into embeddings. These embeddings goes through the convolutions, and finally through the max over time pooling that summarize all the information that the convolution have extracted, and finally the prediction, right, with softmax that returns whether an attribute is present or absent. And if it's present, we save it as present into the table that we have discussed before. This system obtained an accuracy that was pretty high with a known institution and also with unknown institution. If you look at these 2 charts in the slide, on the left you have the known institutions, meaning the institutions on which the system was trained. Of course, the test set was held out at test set, so it was not known during the training, but the institution, yes, was known. So we had some data points of that from that institution to the training. Instead, in the held out institutions means that all the test set was containing data from an institutions that was not represented into the training set. So what you can notice from here, we have 3 settings. One with a single convolutional, with a convolutional neural network trained on a single institution, and one on 2 institutions and one on 4 institutions. So for what concerns that known institution test, you see that they perform almost the same, with the 2 institutions seems like the best performing model. So you get that as the number of data points during training increases, you see they tend to perform equally. Generally, one thing that you may notice is that the system trained on 4 institutions needs more data points to reach the performance of the others. And this is because of the variability, right? You have more variable training data, so the system needs more data in order to understand the more variable data. But then when it understands it, when you get around 4,500 samples, then it starts performing like the others. And what is more interesting, it performs better than the others on new institutions. So what you see on the right side, right? You look on the right side, the 4 institutions needs until 4,500 to get somehow the same performance of the 2 institutions. But after that, they start performing much better. And here you see that also the 2 and the 4 institutions have a performance that a gap with the single institution of about 2% to 3%. And that gap is very relevant, because when you speak in healthcare, 2-3%, you're actually affecting the life of quite a few people. Thanks to this system, we had a lot of benefits. The hospital in particular had a lot of benefits, because the studies that were done before, they were based on about 300, 600 patients. And now, thanks to our system, they're based on 6,000 patients. And again, you remember the picture of the Mona Lisa. If you look at 300 patients, definitely you have a low resolution picture of the disease. But if you look at 6,000 patients, you have much better and higher resolution picture. We expanded the system also for other organs, for example, brain, lung, pancreas, prostate, and so on. And it is currently utilized by MGH. And then I'd go to another project that was carried out together with Dana Farber. This project was about improving the patient selection for cardiac resynchronization therapy. So cardiac resynchronization therapy, or CRT, is a very risky procedure that is done to people with very serious cardiovascular problems. And this procedure not always succeeds. Let me explain you. So it's very risky for the patients, and it's also very expensive. 1/3 of the patients do not benefit out of it. Actually, a subgroup of them even die for comorbidities and complications. Whenever they do this procedure, there is a window of about 18 months for the assessment of the procedure. And that's the period in which you can see who is benefiting out of it or not. So when we were working on this, we tried to get that from Boston hospitals, because this was done while I was in MIT. We got about 1,000 patients, 990 ones. Each of them had about 75 nodes. Their distribution was 78% male, 21% female. And their average age was 71 years old, and they were mostly white. We quantified whether they benefit or not by looking at whether they had an improvement in the left ventricular ejection fraction, which is like a way to measure, in fact, if there is an improvement or not. If there was not a change in this LVEF, we consider the patient as not improving. Otherwise, yes. Also, we consider as not improving patients that died within 18 months from the procedure. So to, again, what we had to do is to exploit both unstructured and structured data. So we combine the unstructured data with the structured data, and the type of information that we utilize are listed here in the slide. You can see there are demographics, past health services utilization, billing codes and country information, laboratory values, medication, clinical information, and EHR narratives. All this data was put together, transforming to a long vector, and this vector was fed into some machine learning systems. Of course, we did the classic split, 80% for training, 20% for testing, and we utilized several classifiers, logistic regression, support vector machine, random forest, and extreme gradient boosting. As you can imagine, extreme gradient boosting was the best performing algorithm in this case. And here you can see the results. What is very interesting is that we could identify 26% of the people that were not going to benefit out of this procedure in advance, meaning that actually we could have a benefit in their life because they were not basically going towards a procedure that would have been far too risky for them. And you see this represented on the image on the right. You see there are 100 people. You see the blue ones are those that are not going to benefit, and the pink ones are those that we were able to identify. The system had a 79% precision, which is somehow reliable. I think in the future we need to improve on that, but it was like a very good starting point. So going towards the conclusions, as I always say, there are no conclusions here. We have just started, and there's a lot that we need to do still. If you look at what's the expenditure of the US for healthcare is about 17% of the GDP. Which turns to be $3.7 trillion, like really a lot of money, about over $10,000 per American citizen. Out of this 17%, 5% comes from private insurance. So you can see that on the right side of the slide. So, so with this, such an expenditure, you can understand the benefit of improving the healthcare and why there is this really strong need of putting healthcare like in a value-based paradigm where the clinical institutions are rewarded on the basis of how they can reduce the cost and improve the outcomes. So there is a very big attention to this in the United States, and I suppose this will happen also in Europe very soon. NLP in this respect can handle the constantly growing clinical data, can help to structure and complete the EHR even during their creation, so that doctors don't need to waste 51% of their time. It can help to improve the retrospective studies. It can support, as I was mentioning before, the value-based care, which is based on the idea of prevention, early diagnosis, and drug discovery that is somehow very focused on the individual. Just to speak about drug discovery, I think that developing a drug takes about $2.6 billion for a period of 8 years, and 9 out of 10 drugs fail during the period in which they are tested in the clinical trials. Meaning that if we can optimize this process, definitely we can go very far. And of course, the personalization and individualization of the healthcare is another crucial topic, thanks to the genomic data and so on. So given all these opportunities, you can imagine why natural language processing in the next year is going to pass from $1.5 billion of revenue to $3.7 billion, yes, with a compound annual growth of 20.5%. And the US will lead, but as you can see from this chart, also Europe and APEC will follow this trend. So that's all from my side, and thanks a lot.
Enrico, thank you so much. It was very, very interesting lecture. Wow. Thank you. Guys, do you have questions? You can unmute. You can write your questions in chat, or you can unmute and say it.